we get started talking about the Intellietch program, I'd like to just spend a minute or two talking about our company, Intellisense. And so Intellisense, we were founded in 1991, and we are a MEMS company based in Boston, and we are one of the leading vendors of different simulation tools for MEMS designers and MEMS researchers and MEMS lecturers. And we have many areas of expertise ranging from MEMS sensors and actuators to RF MEMS and optical MEMS, as well as microfluidics and bio-MEMS. And we also have a very strong expertise in process simulation as well, and that's what we're going to talk a little bit more about today. So Intellisense, as I said, was founded in 1991 as a spin-off from MIT, and we were had a foundry here at our location in Massachusetts for several years. So we gained a lot of process experience at that time. And we also had a lot of experience developing devices ourselves and experience doing wet etching. So at the same time we were developing those devices, we were also developing the MEMS software tools. In 2000, the company was acquired by Corning. But then a few years later, it was acquired back from Corning and became private again. And really since 2004, we've been focusing on the MEMS software tools and putting a lot of effort into making those the best they can be, making those capable of doing more things than we can find anywhere else. And that's really our focus right now. Especially our focus is on process simulation tools, making things easier for MEMS designers when it comes to process, when it comes to designing the process, and doing a lot of modeling before going into the clean room in order to save time and save cost. So as I mentioned, we have the MEMS software and also the fabrication and design services. Within the software tools, we have a large suite called Intellisuite, and this suite includes anything from the process simulation, which we're going to talk about today, to more system-level simulation, microfluidic simulation, thermo, electromechanical, multiphysics analysis, and layout, and a few other tools as well. And as far as development of hardware devices ourselves, we've done a lot of work developing our own devices, as well as we have design and fabrication services for other customers. So we do design and fabrication also for some of our other customers and universities and companies that we partner with. So our operations, we are headquartered in Boston. That's where our main location is, and we also have a large facility in Nanjing, China as well, which is where we currently have about a 50,000 square foot R&D facility, which also includes a clean room. And this is where we do a lot of the we do a lot of work ourselves in making sure that our simulation tools are benchmarked and making sure they're accurate. So we've really put a lot of effort into ensuring that the simulation tool, specifically the wet etch simulation tool, is the most accurate simulator possible. Now today we have customers in over 30 countries, all around the world, from Europe to Asia to North America. Some of our customers include some of the largest companies around the world which are working on MEMS, as well as we have a large amount of academic partnerships as well. So we're working with many universities around the world, as well as universities in North America, including the University of Michigan. And for our academic partners, really they enjoy using the software on one hand for teaching. A lot of professors are using the software in introductory MEMS courses to teach students about anisotropic etching and other MEMS processes, and to allow the students to actually visualize what's going on in the MEMS process. And on the other hand, a lot of researchers, academic researchers, are using the software in their research projects, really to help them speed up the design cycle and save time and save costs in the clean room. And in addition to having our own clean room, we also have a lot of affiliations with other foundries and other MEMS industry partners as well. And finally, just a few notes on a few awards we've achieved over the years. We've really put a lot of effort, as I mentioned, into making the software the most accurate and highest quality tool that we can, in order to really help our partners with their teaching and with their research work. Now specifically, Intellietch is what we're going to talk about today, and this is our flagship tool for wet anisotropic etching of silicon. And this is a really powerful tool, which I'm going to show you in a few minutes, because it really has a lot of capability as far as simulating structures that have multiple steps and multiple different masks. As you see here, this is a comparison between simulated microneedle array fabrication on top and some simulations within Intellietch on the bottom. And so you'll see this is a 4-step process with 4 different masks, and having a separate etch between each mask step. So for simple etching simulations, as well as complex simulations like this with multiple steps and different combination of processes, Intellietch is really powerful. As I mentioned, we've really validated the simulator, spent a lot of effort benchmarking it. So you'll see here some of the different experiments that we've done to compare the simulation results to the results in our own clean room. And one other advantage of Intellietch that really sets it apart from other tools is the capability to do higher order plane etching. So as opposed to simply being limited to some of the standard silicon wafer orientations, in Intellietch you really have the freedom to etch whatever higher order plane you'd like to, and this really opens up a lot of possibilities. But probably the best way for you guys to really get an idea of what Intellietch is about is for us to take a look at the software itself directly. So you'll see here I have the Intellietch program open. And what I want to do now is just take you through a simple example of how to use the program, just so you get an idea of how the software is used and maybe get some ideas on how it could be helpful for you in your research and teaching. So to start out, when we're using the program, we're going to be defining usually a certain silicon wafer. So as I mentioned, we have these predefined surfaces here. So if you're using just a standard 100, 110, 111 wafer orientation, you can select those. Or if you want to do a more advanced surface and etch a higher order plane, you can simply put in the orientation of the wafer, input the Miller indices in these boxes here, the HKL Miller indices, and then it'll generate, it'll generate a wafer of that orientation for you. And we do have capability to etch quartz as well. Most researchers are doing silicon etching, so that's mainly what the program is used for. But it is possible to do anisotropic etching on quartz, and we're also adding some other materials, capabilities for other materials as well. So once we have our wafer orientation defined, then we're going to go ahead and put in the dimensions of the wafer. So in this case, I'll put in a length and width of 250 microns and a thickness of 22 microns. And you'll see this NOC value, that's just kind of a resolution setting. So obviously, as if you were to just want to run a quicker simulation, you can set the resolution setting lower. And if you'd like to get a more accurate simulation, you can set the resolution a little bit higher. And just know that the simulation might take a little bit more time. But really what's powerful within this simulator is that simulations run through very quickly, as you'll see in just a few seconds. We're going to be able to get some results, which is another one of the really powerful aspects of Intellietch. In addition, one option you have is inserting like an SOI layer down at a certain depth in the silicon wafer. So if you had some kind of doped layer within your wafer, you could set that up as well. So you'll see then that we have this wafer generated with our desired orientation. And the next step is going to be to apply a mask onto the wafer before we're going to do any etching on it. Now, the way that you would apply a mask in the program, the first step is that you would need to import your mask file from whatever program, whatever layout program you're using, and import it so that you can use it within Intellietch. So to show you how to do that, I'm just going to open up our layout editor for a few minutes. This is our layout editor called Blueprint. And Blueprint is automatically included with Intellietch because it's needed in order to import the mask files from other programs. Or if you'd like, you can simply draw your mask layout within Blueprint here. But in many cases, people might be importing, say, a GDS file or a DXF file. And that's very easy to do. All you need to do is just select your GDS file and open it up within Blueprint. So you'll see this is just kind of a simple square and a mask layout. And once you open up your GDS file or your DXF file, in the case that you wanted to import it from another program like LEdit or AutoCAD or something, then all you need to do is just export it into our IntelliMask format. And just save that mask file, and then it'll be ready to use within Intellietch. So if we go back into Intellietch then, once we have that mask file imported and saved in our IntelliSuite format, we can just go ahead and apply it on the wafer here. And so in this case, we would select the file that we want to use. In this case, we also have possibility to use like bitmap files as well. So we would select our mask file, and then we've got it ready to be applied on the wafer here. Depending on if you want it to be a negative or a positive mask, you can flip that back and forth as far as exactly whether you want it to be negative or positive. If you really wanted to, you could actually use these drawing tools, and you could draw right within this mask window. So you could just draw some shapes quickly. You can draw different shapes quickly within this mask window, which is obviously a little bit less accurate. In most cases, you're probably just going to want to be importing your mask file. But we can just take that away as well. And then you're going to be applying it on your wafer. And now we have two different options for applying the mask on the wafer. In this case, we're going to just keep it as being defined as silicon nitride. But you can choose between silicon nitride or silicon oxide as well. And the materials don't really have any difference in the simulation. They're both going to be considered as just to be a hard mask. So within the etching simulation, the actual mask material is not going to be etched away at all. It's just going to be considered a hard mask. But having the option to define the two different materials will allow us to apply different masks on top of each other, which we're going to do in just a minute. So you'll get a better idea of how that might work. But in this case, we have our mask, so we're going to apply it on the top of the wafer. And we're just going to click this button to apply it on the top of the wafer. So you'll see that that little circle is going to be applied on the wafer, and you can see it in red there. So what we're also going to do is apply some masks to the bottom of the wafer. So you'll see I can just flip this over so we can get a look at the bottom. And we're going to open up a different mask. So you'll see we have this different mask shape, and we're going to select this button over here to apply the mask on the bottom. So you'll see that it's going to be applied on the bottom there. And finally, we're going to apply one more mask on the bottom, which is going to cover the whole bottom of the wafer. And in this case, we're going to use the oxide material. So that's going to be applied on the bottom. But you'll see it's not going to be applied over the nitride material. It's only going to be applied on this bare silicon part of the material here. So now that we have all of our masks applied on the wafer for right now, we're going to go ahead and start up the wet etching. And now to start up the wet etching process, we are just going to go ahead and open up this window here. And here we're going to select whether we want to etch the wafer by a certain time period, or we can also etch down and define a certain depth that we want to etch down to as well. In this case, we're just going to etch a certain time period, 17 minutes for this first step. And here we're also going to put in our wet etch parameters for the recipe that we're using. And we have a database here, some of the common different recipes that might be used. In this case, we're going to use KOH, 40% concentration at 70 degrees Celsius. But we have some different concentrations here, also some different concentrations for TMAH, as well as TMAH with a surfactant, or KOH as well. And these are just some of the common recipes included with here. It's also possible to If you're using a recipe that's different from one of them listed here, it's also possible to calibrate your recipe and add that into the software as well. That's something that's easy to do. So then we're just going to go ahead and start simulating. And so you might be able to see the software kind of moving as we run the simulation. As I mentioned, it ran through very quickly, and you'll see here that after we've done the etch, we just have this little tip underneath that circular mask shape. Now what we're going to be doing in the end is we're going to be creating an AFM tip in this example, and a cantilever for an atomic force microscope. That's the structure that we're going to be creating out of this wafer. And so this tiny little tip here is just the end of that cantilever tip, which is going to be used with that atomic force microscope. So now the next step is we're going to be applying a different mask. So if we go back to our masks menu, I'll drag it over to the side so you can see the wafer as well, but we're going to remove this mask that we have on top right now. So we'll see that mask gets removed there. And we're going to go ahead and select a different mask. And we're going to apply that on top instead. So you'll see this new mask is applied on here, including on top of this feature that we created. So that's a little bit what I was talking about in having this tool being very useful for multiple step etching processes with multiple different masks. This functionality makes it easy to simulate a lot of complex devices that can be produced by wet etching. And so if I go ahead and go back into our wet etching menu, then we're just going to go ahead and continue the etch that we're doing. In this case, we want to use the same recipe, and we're going to be etching this structure for 11 more minutes. So we've already etched it for 17 minutes. That's what's already been done before, so we're going to go ahead and put in 28 minutes as the total time that we want it to be etched. And we'll just go ahead and simulate that as well. So you can see if we look at the wafer here that we've done some more etching that's being protected by this mask, and we've still got those masks on the bottom layer, so nothing's happening on the bottom layer yet. You can also see here too that the different operations that we're doing are showing up in the message window on the left. And so this is showing us that we're applying our different masks, and we can look at which mask files we're defining. We've also got a record of what etch recipe we're using and how long we're etching it for. Now, one thing that's an option sometimes is the question comes up: can we say go back to what we had before? Say go back to where we etched before we etched in this step. That's not something that we can do directly in this structure that we're working with. But one thing that's easy to do is we could save the simulation at the current point that we're at right now. So we could save the simulation and freeze it right here, and then maybe we'll go on and do some more, do some additional etching steps. And if we wanted to come back to the point that we're at right now, we just have to open up that simulation file that we saved. So say maybe we want to go ahead and just save that simulation. We can save the simulation right here and come back to it. But in this case, we're going to move forward, and we're going to continue to change the masks up a little bit and continue doing some wet etching. So what we're going to do then, the next step is we're going to just go ahead and, on the bottom side, we're going to remove this green oxide part that we have. So we're going to click over to the oxide and say that we want to remove that from the bottom layer. And so anything you see the color blue here is just now the unprotected silicon wafer, which we can go ahead and do some more etching on. So now we're going to go back into our wet etching window and etch for an additional 7 more minutes. Go ahead and simulate that as well. You can see the simulation progressing there in the progress bar, and you would also see that the GPU memory bar. One advantage of Intellietch here is that we can access the GPU memory within the computer's graphics card, which allows for the simulations to run through so quickly as you're seeing here. So one thing that you're going to need in order to run this version of Intellietch, this GPU version that's going to access the GPU memory, is you'll just need to make sure that you have a CUDA-enabled graphics card from NVIDIA. And if you had specific questions on those graphics cards, you could feel free to email us, and we could give you some more information on exactly which graphics cards will give you the best performance. So now you'll see it etched away to provide us with our final structure here. So what we can do right now is just go ahead and remove the masks so that we can see the structure. So remove the mask on the top and on the bottom. And so you'll see that what gets created through those 3 steps is this atomic force microscope tip, as I mentioned, so this AFM cantilever tip, with just this tip on the end of the cantilever structure right here. And so once we have our final structure created here, we can do a couple different things to look at it. One thing that we can do is we can take some measurements of the structure. So say if we wanted to use this measurement tool and measure the distance between 2 points. Say if we wanted to measure the length of this cantilever tip from the base here, we can measure that, and you'll see it gives us the measurement here. We can measure exactly just one certain point and give us the coordinates of what that one point is on the structure. And we can also say if we want to look at the orientation of one of the planes that we've etched here, we can just go ahead and say if I wanted to look at this plane and determine what orientation it was, we'll see that this plane that's etched here is this -1, -1, 1 orientation. So that's a useful way to, when you're etching a structure, to look at which planes you have. So those are some different things that you can do with the measuring the distances, as well as, say, measuring the angle between 2 planes is something that you can do as well. So say we want to look at a cross-section of the structure, which is useful a lot of the times when we have a complex structure and can't really see what's going on inside of it. We can go ahead and look at a cross-section. And to do that, we simply open up this cross-section menu. And we can say that if we know the certain coordinates that we want the cross-section plane to run across, we can input those in here. Or we can simply select 2 points on the figure that we want this cross-section plane. So say if we want to just look at a cross-section right across the middle here, I can just select the first point on one side and the second point on the structure that I want to look at, and it'll generate the cross-section plane right around that point. Say if we want to flip it around and look at this side of the structure, then maybe what we'll want to do is potentially look at the view just from one side. So you see that's something we can do easily here. Say if we wanted to measure the height of this cross-section tip, we would just look at this view from Y is what I selected. And then we can go ahead and use our measurement tool. Select the 2 points and look at the height of that cantilever there, of that cantilever tip. Or in this case, we're looking at on the opposite side of that cross-section that was defined. So as I mentioned here, those were a few different options for the projection of the structure, which you can use to view it. See, there's a couple different views that we can use. Another thing, going back to the view, there's a few different options that we can look at for viewing the structure, as far as just looking at the structure as the individual cells that we're using, or as more of a smoothly shaded structure like we were looking at, just depending on how we want to look at it. And then, because one thing that we can also do is export an image file. We can export a JPEG file of this structure here. And as far as the export, it is technically possible to export this structure to like a mesh, to a finite element mesh, but just in the fact that there will be so many of these small features, so many of these small etched features, it's not really feasible to export this to a mesh and then go ahead and do some multiphysics analysis on it. If you wanted to be exporting things from meshes, it'd probably be a better idea to use our other tool called Intellifab, which is going to be the topic of a webinar next month, which we'll be talking a little bit more about IntelliFab. But within IntelliFab, it's a lot easier to do MEMS process simulation, and in this case, wet etching is just one step of that simulation. But that tool makes it a lot easier to go ahead and export a mesh for analysis. Here within this tool, Intellietch is really for people that are focused on wet etching and want to look at how different mask layouts are going to affect their final geometry, different mask designs, and also look at how different etch recipes and how different different etchants and different recipes as far as the temperature and concentration and etching time and all those process parameters. See how all those different process parameters are going to affect the final structure, as opposed to going in the clean room and running several experiments to try to test all those different iterations out. You'll see that here within the software it makes it a lot easier to simply import a mask and build up the recipe and run through many different simulations, many different design possibilities quickly. And you may have also seen here this DRIE etching option. This is not going to be the full DRIE simulation within this module. We do have some other tools for dry etching as well, simulating dry etching of silicon. But in this case, in Intellietch, it's more of an approximation. It's really just going to etch down. If you apply a mask, it's just going to etch down, directly down to a certain depth, and you're just going to have perfectly vertical sidewalls. So you're not going to be looking at all the dry etching effects, such as the sidewall scalloping or the etch lag that comes along with DRIE. For that kind of thing, we have other tools, as I mentioned. Recipe is our main dry etching tool, as well as the IntelliFab and FabSim tools. But here within Intellietch, we included just to have kind of a nice approximation if you're going to be combining, if you want to just combine a simple vertical etch like that, as well as combining it with your wet etch steps as well. So in that case, that's a little bit of an overview of this example here within Intellietch. As you'll remember, we took things through the initial setup and the initial import of the mask, all the way through to the defining the wafer orientation and the wafer size, then going and applying some different masks on the structure, applying masks on the top and the bottom of the wafer, and using the different material definitions to apply multiple masks at once. And then you guys saw how we can go ahead and do multi-step etches with multiple different masks, and seeing how to do that. And then after the simulation was completed, looking at different post-processing elements as far as measurements and cross-sections and some of the different ways that you can look at the results and look at the geometry and look at some of the different exposed planes and some of the different things like that.